Okay, everyone, welcome back to the class. Uh, First of all, as a courtesy reminder, we have a homework one due, I believe, tonight. So it's 11:59 p.m. MDT. I mean, my time zone's MDT. So now it's 5 p.m. I have not received a submission from all students in this class. So if you have not submitted the homework one, please do it, submit it to me ASAP. Email everything's, inside. Okay, so let's start our lecture today. So today we will try to finish two topics, lecture 7, naive Bayes, and the lecture 8, logistic regression. So first, naive Bayes. Recall that in the last lecture, we finished the k-nearest neighborhood algorithm is a very simple but powerful algorithm for classification. Today, naive Bayes is another simple and fast classification methods. It is based on the Bayes formula. First of all, I assume everyone has already known what is Bayes formula. As a very quick review, it is, let me give me 1 second. Let me make this one. Okay. So this is nothing but a conditional probability formula, which is, just the definition. PA given B equals to PAB divided by PB. In some textbooks, I don't know the textbook you use. In some textbooks, they use PA intersection B. Here is just to make my life easier. I didn't put intersection. I just put A comma B. And A PAB using this conditional probability formula again, it's PB given A times PA given to divided by PB. So here we call this PA given B as the posterior probability. This PB given A is the likelihood, PA is the prior probability, and PB is the support, or you can call evidence something. In many applications, since B is given, this PB will be a constant, and hence later we'll see those kind of mathematical formulas. This PB will somewhat be ignored because it's a non-active constant. What we focus the most is the likelihood PB given A and the PA. And I know many people may be confused, or let's say may not quite understand. So this is just a formula, beautiful, but so what? What's the meaning? Well, the meaning, the very important thing is B is something that we observed today. And I want to know given this B appeared, what's going to happen to PA? Let me give you a very quick example because I hope everybody can understand instead of just a know the formula itself. I mean, it's just a mathematical notation. What's the meaning? The meaning is the something behind this formula. It's actually something like a philosophy. So let me give you a very simple example. Let's say B is a signal. I'm talking about like in algorithmic trading. Let's say, let me just randomly pull something. Let me just let's say when we do stocks, we of course want to earn money, of course. Let's say suppose consider this trade, this pattern, this zigzag but increasing pattern. You can see, for example, here we have the tops. No, I should have plotted a straight line. Sorry, my hand cannot just, suppose we see this pattern, which is we have, you know, one, two, three such a waves, right? Okay, in each, the top of the wave is increasing and the bottom of the wave is also increasing. Okay, so now suppose I am at this point. Suppose I'm now at this point here. Question, what is the probability that tomorrow it will increase? Of course, stocks I want to buy at low and sell at high so I can earn the difference, right? Okay, so in this case, we can say that B is the appearance of this, let's say three zigzag, this, the button at the top of the wave, and A is the case that tomorrow it will increase or decrease, whatever. So the interpretation of Bayes formula in this case is okay. Now I'm gonna look back at the history. instead of what just occurred. Let's say this is yesterday, the day after, before yesterday, 2 days, 3 days before yesterday, 4 days before yesterday, something like that. I'm gonna have a look, do the back test of let's say for example 10 years, for example, and then I'm gonna see, okay, A is what? A means increase. So among 10 years, what is the probability that tomorrow the price is going to increase? And then PB given A is what? A is increasing, meaning that among all those kind of given increasing past historical data of the stock prices, what is the probability that these are three times of zigzag gonna occur? And then divide by the probability of PB, which is among the whole 10 years, let's say this zigzag occurred. In other words, I have changed the whole thing so my posterior probability is given that, let's say yesterday, the day before yesterday, the day, 2 days, 3 days before yesterday, I have already observed that this time shape of the stock price just, I just observed. Given this question, the probability tomorrow it will increase. I've already converted to be the likelihood times the likelihood times the prior, where the likelihood is by the past data, do the back test, given that stock price increase. The probability, the three, zigzag, this pattern, occurs times the probability of PA, which is increasing, divided by the probability of PB, which is this pattern shows up. So this is the meaning. It is actually based on the past, which is now something occurs. Then I try to, find the past such situation. And that's the reason why B given A is called a likelihood. And A is a posterior, so the prior, and the PA given B is a posterior. Okay, so one thing I do want to mention is the chain rule of conditional probability, which is this. So suppose I'm interested in, again, here I use comma instead of intersection, events A1 to AP. Suppose I have probability of A1 and A2 and A3, blah, 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 and AP. This equals to, remember, we can use one time of conditional probability, which is take PA out, and then times the remaining, which is P2 times, sorry, PA2 till PAP given PA. And then similar things for the second item, I can use one more time of conditional probability, which is PA, then this P2, take it out, P2 given PA, then from 3P3, sorry, from P3A3 till till AP given A1 and A2. And I just continue doing it again and again. And finally, I will have this formula, which is I take the P1 out, and for all other things, I will have a product. I hope everybody is familiar with the product and the product and also summation, product is pi summation sigma notification. That means I'm gonna have P A2 given A1 times PA3 given A1 and A2 times blah, blah, blah until the last item, which is PAP given A1, A2 till AP minus 1. So that is the chain rule. We will use this several times in today's class. Okay, so first, the idea of the Bayes formula. So it's something very similar actually to KNN, k-nearest neighbor. Uh, so consider a classification problem where the features, sometimes we call the covariates, just to let you know, the features covariates, they are all the same, are representative by random variable x. For convenience, for notation consistency, we use the same notation, which is p, meaning that the feature of x always has p, the vector always has p elements, p features. X is in RP, and the corresponding class label is representative, denoted by a random variable y. And again, using the same notation, we assume it has m classes. The label going to be from 1 to m. Okay, so now let the pair xi, yi, be careful, x is a vector, y is a scalar, and be the ith training data point. And this, you can see when we write the big one, that means it's a random. When we write a small one, that means it's a realization of the random. So let this be the ith training data. So now for a given target vector x, which is unknown, And the Bayes classifier predicts its label by choosing the class with the highest posterior probability. Mathematically, we're writing this way, and this is the posterior probability, which is the probability of y equal probability the label equals to a specific y given x equal to x. This means what? This means, okay, I've already observed this x vector. For example, x can be like, just remove it, like some pattern of the stock chart. It can be, let's say, an image. I've already observed this image. Question, what is the label? The label in stock market can be, for example, decreasing, increasing, or just, nothing happens, you know. And for a picture, the label, remember, like a cat, a dog can be, an identification of the object. And then we will choose the class with the highest posterior probability. In other words, if you consider like the KNN versus this, the only difference is that this one, Bayes classifier, we're talking about, in the probability space instead of just the distance space. And later we'll see it is quite similar to actually YNN, the meaning. Okay, so we will see more details about it. Here's one point I want to mention. In simpler term, this means predicting the label that appears most frequently among the training data points that have the same, be very careful, exactly the same feature vector X. So here is an example to show how we indicate it. So now suppose we have, we want to predict a person's gender based on their height and weight. Okay, now I have, where it is? Yeah, now I have some data here. Suppose -1 is female, +1 is male. So this height is in a centimeter, weight is in pound, and I have all these 1, 2, 3, 4, 5, 6 data. Again, in the real example, you will have probably way more than 6 data. Here's just a example to show the idea of Bayes classifier. Here we're talking about Bayes rather than naive Bayes. Later we will introduce why we want to include the naive Bayes and what does naive mean? Why do we need it? Okay, so now suppose I have a target data, which is x equal to 165, 130. Again, pay attention. Each training data should have a vector of x and a label of y, okay? So for example, the vector of x in the first data point is 165, 130. The label y is -1, meaning female, okay? So now I'm asking, I observed a new person whose height is 165 centimeters. 165 is about 5'5", I guess. I'm not pretty sure. I guess a 5'5" to 5'6". It's a 5'3" to 5'5", approximately. 130 pounds. Question, what is the gender? Okay, so now I'm gonna find exactly the same 135, 165, 130. Okay, here I have 165, 130, 165, 130, 165, 130. Okay, so now see it? I have three data, right? Among these three data, two are female, one is male. So according to here, with the highest posterior probability. In other words, the chance of this person to be female is 2/3. The chance of this person to be male is 1/3. And then we will predict the gender to what? To female. Why? Because 2/3 is the highest posterior probability. Okay, similar things. Now suppose the person's height and weight are 182, 180. Question, what is the gender? What would you predict the gender of the male, of the person? Actually, the answer is male. Okay, we will see the data. Okay, 182, 180, 182, 180, 182, 180. And the similar things, we have three data points in the training data set. Among these three data points, two of them are male, +1. One of them is a female, -1, and hence I will classify this data to be what? To be male. Why? Because 2/3, which is the highest posterior. Very simple, right? So this is the basic concept of Bayes classifier. And here more notations. Originally this class was taught, as an undergrad class for that's why I had a lot of mathematics and notations here. But to be honest, since this is a class for certificate, uh, I still want to keep this. The main reason because I want people students understand some points clearly. However, let's say if you really hate mathematics, you can skip most of them. However, do not skip any examples or any of those kind of explanations because it's really, really important. Because the idea of this is I want to, after the class, what does, for example, naive Bayes or Bayes classifier mean instead of just know, oh, it's a classifier. So why do you need to use naive Bayes? Why don't you use, let's say, KNN? Why don't you use, for example, SV, let's say, support vector machine later we'll introduce? I don't know. I mean, I don't want this occur. At least I want everybody knows the ideas of everything, and hence I still include this. Okay, so more formally, for formally, we estimate the probability of event x equal to x and y equal to 1. Again, I use comma instead of intersection. So this don't be scared about the mathematical notation. Looks like so many things. Actually, super simple, which is just the number that it occurs divided by the total number of m. You see what I mean? Say, for example, suppose here I'm gonna ask you, hey, what is the probability that x equal to 155, 130, and y equal to exactly 1? So simple. How many data totally? Which is what is my m? My total data is 1, 2, 3, 4, 5, 6, 6. Okay, n equal to 6. Then you just need to see how many data are 165, 130, and gender equal to female. 1, 2, right? It's only 2. Okay, so the probability is 2 over 6, which is 1/3. Done. You see what I mean? So this is just the probability, the total number that this x equal to x, y equal to y occurs over the total number of training data. Done. Super simple. And here I do have a delta indicator function. So there, the delta of with some conditions equal to 1, that means all the conditions satisfied. For example, this means xj equal to x, xi equal to x, and y equal to y. So for example, again the same thing. Let's say my x is 165, 130. In other words, among all these 6 data, I'm gonna find, how many data are the data such that the height is 165, the weight is 130, and the gender is -1. That's it. If this one is satisfied, then this data are gonna be +1. If let's say here it's not satisfied, then this data are gonna be +0. And this is the indicator function. That means delta equal to 1 if all these conditions retain in the subscription, if they subtitle, sorry, if they are all satisfied. If one of them is not satisfied, it doesn't have to be all. As long as one of them is not satisfied, then delta equal to 0. So now with this one, by Bayes formula, we just substitute everything. And then both numerator and the denominator will have a constant 1 over n, and they're canceled. And then you will have this. So again, this is super simple. It's just by frequency. Use frequency to estimate the probability. Done. So now finally, again, as I just mentioned, the Bayes classifier assign this target data point x to the class with the highest estimated posterior with this one. So here I'm going to compute which is the probability of y equal to 1 given x, y equal to 2 given x, till y equal to m given x. And then I'm going to, because I have m classes, I'm going to see all these m classes to see which class has the highest posterior. And then I'm going to assign this target data to this class down. And that's one thing I just mentioned for a given x equal to x Bayes classifier is actually equivalent to KNN classifier with k equal to m. Just now I said k equal to 1, which was wrong. Should be k equal to m, okay? The only difference is that here the distance is the probability space instead of the Euclidean space. So yeah, that's the thing. Okay, so people will say, oh, that's so good. So simple, right? I love it. Unfortunately, Bayes classifier, yes, the idea is very simple, direct, and people love it. But unlike KNN, in the real world, Bayes classifier typically does not work. Does not work. Why it does not work? Because one big challenge of the previous example in the previous demonstration of the whole mathematical thing is that it requires the exact match of x equal to x, meaning that Suppose I have P features. It must be x1 equal to x1, small x1, x2 equal to small x1, xp equal to small xp. So everything exactly match. You may say, what's up? It's easy, right? So for example, everything exactly match means the height must exactly be 165. The weight must be exactly 130. It's so simple, right? No, in the real world, it's not that simple. The reason because if the feature number p is large, trust me, in some cases you could have p like a million once, and the chance that you observe exactly the same feature vector x in the sample data, it's actually very low. What's gonna happen is, remember here we just got this posterior estimate Bayes formula, right? In other words, this one will be invalid. Why? Because this item in the the denominator delta xi equal to x. If my p, the number of features very large, this one will be zero because you cannot find even one, sample exactly every feature exactly match. It's very low. As a super simple example, say I want to predict, the gender. Suppose we consider here instead of two, I consider seven features: height, weight, age, nationality, occupation, parents' height, parents' weight, something like that. Okay, now suppose I have 1,000 random sample from people worldwide. I'm gonna ask you, hey, what is the chance that among these 1,000 data points, 1,000 people, two individuals share exactly the same value across all these features? Think about this, because they need to have the same weight and height, easy. Age, not that difficult. Nationality, it's already, because I'm gonna randomly, get samples, from people worldwide. Nationality is already not that easy. Not to mention, you need to share exactly the same occupation, exactly the same parents' height and weight. Think about it. The chance is super low, and then this number becomes zero. Then immediately it fails. So what's the point? I mean, mathematically everything's so good. What's the point if it doesn't work? Meaningless, right? Okay. So that's the motivation of the so-called naive Bayes instead of the Bayes classifier. So the naive Bayes classifier solved this problem by introducing a very simple assumption. But this assumption solves the whole issue and makes this classification super easy and super powerful. The to have a look at this, we need to mathematically see the problem again, which is to explicitly, you know, uh, figure out this part. Okay, so let's have a look. Again, we use the conditional probability formula. So P y equal to x equal to x given y equal to the posterior given x equal to x. This is equal to intersection of these two divided by the support. And here I ignore the support, which is using this notation proportional to the y, because this support is gonna be a non-zero constant. Why it's a constant? Because x equal to x is given. It's a given thing. For example, this probability is 1/3. It's 1/3 already. You've already observed it. And here, where we are gonna get to the argmax, those positive constant can be simply ignored. Okay, so now I ignore this one, so I only keep the numerator. So and then I will write explicitly for this x vector equal to a small x realization. That means x1 equal to x1, x2 equal to x2, blah blah till xp equal to xp. Okay, so now we use the chain rule of conditional probability. Remember, which is right here, this one, and then we expand it, which is we take out the first item, then which is the product from the second item, which is this one. Okay, so now, clearly the problem's here, because to compute y equal to y, it is linear, super simple. Let's say you have 1 million data, 600,000 are female, and that's 400,000 are male. So what's the probability of male? Simple, 40%. Female, 60%. Extremely simple. The problem is here. You need to find exactly where it is. Wait a minute, which is here. You need to find exact match x equal to x. This is the key issue, because if p is large, it's almost impossible. And hence, the problem is clearly this, the multiplication, I mean, this part. Then how to fix it? So here comes the naive Bayes assumption. In the naive Bayes, we simplify this by assuming that given the class label, let's say the label was Y, the features are mutually independent. Since they're mutually independent, now I don't have to include everything here. I can simply just include the one down. Why? Because they're independent. Recall the definition of independency. Let me just write here something. So consider I have, let's say P A given B. Let's say given BC. Okay, right? Equals to P A given B. If events C and A and C, A and C are independent. See it? So this is the definition. And hence, they're independent, so who cares with or without C? I just remove it. Okay, similar things here. So here, where it is? Here, assuming that for a given label, features are independent, and hence, for the probability xj equal to xj, given y, all these can be ignored. All these, x1 equal to whatever, and xj minus 1 equal to whatever, xj, they're like this c in the formula. You see what I mean? I can just drop them. Who cares? While this b is, here, what is that? While this b here means y equal to y. And hence, immediately, so many, exact match becomes only one item, which is y equal to y. And hence, I immediately have this. The probability, the posterior is proportional to py equal to y, and then the multiplication of x equal to x and y equal to y. This not only people say, oh, the length of this is shortened. Yeah, true. But the significant point is that instead of find exact match for all the P features, I only need to have the match for the label and a match for one feature. In other words, all these P features, I can separate them to be itemized. So that's the significant point of this naive Bayes assumption. So this makes the calculation much easier and really practical instead of, as we just mentioned, that it's a naive Bayes classifier without a naive. It's a beautiful mathematical formula, but not practical. So what's the meaning? Naive Bayes is really practical. So again, let's expand it even further. So we have seen this, and then as we just mentioned here, we expand x equal to x, the x vector equal to x realization vector here. Now, by the naive Bayes, we just drop all these, we will have this one. And then we'll take the logarithm. Why? Because the logarithm is what strict increasing function. So under maximization, maximizing the original function is equivalent to maximizing the log of the function. And hence I can log the whole thing, by the whole thing, what I mean here. The whole, let me use another color. Let me use, let's say, yellow color. The whole, this part, okay? So I just take a logarithm of the whole this part, and then what do we get? We get this, right? This is super simple because under logarithm, multiplication becomes what? Becomes summation, and hence product becomes sigma. So you just, substitute. And then the prior y equal to y, super simple by the frequency. Let's say, again, 100 example, 50 male, let's say 60 male, 40 female. Oh, I said 60 female, 40 male, right? Yeah, let's say 60 female, 40 male. Then probability, label equal to female is what? 60%. Label equal to male is what? 40%. Extremely simple. Now the issue is how can I compute this likelihood function, which is given the label x equal to x. There are many methods, but the most popular three methods, depending on different, situations of the feature spaces are these three. And then these are the topics in this lecture. The first feature is called Gaussian naive Bayes, which is corresponding to continuous feature space. The second one is categorical naive Bayes, which is corresponding to category features, which are discrete features. And then the third type is called a multinomial naive Bayes, which is for counting feature space. And if you would like, you can just have a look at here. And then it shows you more such things. Uh, Here I just include some more details actually in my lecture. So first, let's have a look at Gaussian naive Bayes. First of all, assume everybody knows what is a Gaussian function, which is a normal distribution, okay? And in the Gaussian naive Bayes, first of all, when will we apply it? Which is when the feature space for each feature j is R, which is a real number. And so in Gaussian naive Bayes classifier, we assume that each feature follows the Gaussian distribution. And here's a PDF of Gaussian distribution. No worry, you don't have to memorize it. As long as you remember what's Gaussian distribution. And the why Gaussian distribution is very special in all probability theory. Because of what? Because of CLT, central limit theory, which tells you that whatever distribution you give me, even discrete, or even the distribution is discrete distribution, the following condition is still satisfied, which is x minus I'd better show it. There's a Wikipedia. Wikipedia is here. Wikipedia, yeah. So it doesn't matter what distribution it is. This one still no. I just need the simple version of CLT. Yeah. This XS or 1 meter, which is I'd better directly write by myself. X minus mu divided by no. Okay. I'd better say X bar instead of mu because X bar is the estimation. Divided by sigma over where square root of m. This one always follows normal distribution of mu and sigma square. Let me put it to be because we typically estimated mu by the bar x bar. Yeah. So this one always satisfies. That's why normal distribution is so popular because no matter what you are, as long as I compute the quantity in this way, it's always normal distribution. In other words, it can represent if you have enough large space, it can represent almost all distributions. Okay, and that's also the reason why such assumption is makes sense. Otherwise, you say why it's a normal distribution? Why don't you from assume it follows, let's say, exponential distribution? And because of this. Okay, so now if we consider in this way, so for each feature space J, we can assume, we can estimate the mean, which is the mu, in my system here, which is the mu here. Here we call it mu J with a hat means estimated. We can always estimate it by the what? By the number of the frequency in my training data. And similar things for the sigma square, which is the standard deviation. We can always use this way. Okay, the details, if you're more interested, here it is. It is where it is class naive Bayes. It is extensive extensive reading which includes the more details like even mathematical proofs. But I guess for most students, if you just don't know what it is and how to apply it, then you don't have to, because there I even showed hand calculation how to compute everything, so you will know it very clearly. Okay, so here is a Python a Python application. Let me just do it. All right, open the one. Let me see lecture 7. And then oh, sorry. Okay, so in this example, I know no matter what, I'll have to import numpy and import matplot, pyplot, p sklearn dot naive Bayes. Okay, naive Bayes. import Gaussian MB. Okay, now let's have a look at the example. Okay, so in this example, first of all, I generate a multivariate normal distribution. Here's 2D is because I need to plot those points, so it's multivariate 2D. So mu one, mu two, and the sigma one one, sigma one two, sigma one two two, two one, sigma two two. N is the number sample size, and then I'm gonna plot the training data first, and then I apply the naive Bayes classification, and I fit X and Y. And again, if you want to say, hey, how did you really fix, estimate it? Error, the mathematics are all here, and also we're gonna calculate this. Okay. In other words, for each J means each class, each feature, not each class. For each feature, I'm gonna compute this, and it is gonna be for each feature and under each label. Now I'm gonna compute for all y's, which is y from y equal class one to class m. Then I can have what? I can have m such posterior function, right? And then in this m posterior function, I have m values. I classify the target data to the highest value, which is the highest posterior probability. So this is the idea of the Bayes classifier. Regarding the naive, is because here in this step we applied the chain rule in the naive Bayes assumption, and hence, So this is very simple. Let's just do it. So first of all, generate Gaussian distributed training data set. How to spell training? Okay. So now I have n equal to 50. This is sample size, and then x1 equal to mp dot random dot multi mul, uh, multivariate variate no mul multivariate. Oh, here we go. Normal, and okay, I need to cheat. The parameters are 10 10. Then the covariance matrix is 25, 6, 6, 36, and m y1 equal to mp dot ones n. Okay, now I just copy and paste for x2 and x3. Oh, oh, oh. Then what are the active 10? What? 20 and 8, 8, and then here is 8 and 25. Did I? Okay, and then I'm gonna concatenate them. X equal to np dot concat. Okay, again, x is equal to 0 means I'm going to concatenate them by rows. Okay, so now what I'm going to do is I'm going to plot the training data, right? Plot the training data. So plt dot plot x1 or x1 or for y. No, no, I wrote type 1, unbelievable. Okay, huh? What is wrong? Oh my God. Okay, here we go. So this is the basic plot of the training data. And here we're gonna what? We're have G and B. I mean, G means Gaussian naive Bayes training model equals to Gaussian naive Bayes and then model dot fit. So now after fitting, what I'm gonna do, I'm gonna plot the decision regions. To this end, I need to add one more thing, which is from matplotlib dot colors import listed map color map. Okay, so now I'm gonna first generate the mesh grid over x and y plane and p dot namespace x. Here I have, let's see here. I use minus and plus phi. Again, again, the reason I use minus plus phi is because it's here. I'd better plot it. It's here. I want to I want to have some space here. You see what I mean? Because if I don't have this minus plus phi, this point will be around here, the boundary. It's not beautiful. That's the reason. Of course, I mean it's just optional. You don't really have to, you don't really have to take it. So that is the thing. Okay, so now I have what? Sorry, here's a mistake. Fix this. Let's fix dumbing minus phi and x the max plus phi, and I use the 200 data points. So this is XS1, two as something third. Now here's to a generation of mesh grid. Okay, now finally I can use what? I can use p color mesh, right? Oh, well, I meant I to predict. I to predict for the whole plan. Remember how do we do model dot predict? I'm gonna what? I'm gonna first of all make it to be an array, and then use dot make array and then immerse, and then make it to be use Ravel to to make xx1 xx2 these two matrices to be a vector. So we did empty.array here dot t, and then the matrix is gonna be x1 dot ravel, x2 dot ravel. These are all something that all the things that we have already done in KNN. Okay, in the last lecture. So and then I have a boundary color equal to listed map, listed color map, and my colors are light coral, light blue, light green, and the light blue. And so now I can have the P color mesh, XS1, X2, and then here, interesting thing because it's a glitch between different libraries. Here in P color mesh, I need to convert this one back to the shape of this XS1, XX2. And hence I'm gonna have Y predict dot reshape X1 dot shape and CMap equal to this boundary color. Okay, so PLT left and PLT something. Oh, great. The predict one spell, predict. There we go. Oh, there we go. And what's so interesting? Huh. I've run many examples. For almost all examples, it is in this way. For almost all examples in this way, I've never seen something like this. Let me see, did I make any parameters wrong? 10, 10, 25, 10, 25, 6, 6, 26, negative 10, negative 10, 8, 8, 25. Looks as correct. Okay, anyway, we can just run several times to see different. Yeah, this is the more common. And here we can see the naive Bayes point things for this NGMB Gaussian naive Bayes. Okay, and the point again when to use it is if all feature for each feature, the space or the domain of the feature is R, which is any number, so we can use this one. Okay, so the second category we're gonna talk about is called the categorical features. So when we're gonna use this one, it is the case that for each feature J, it's discrete set. Uh, I mean, for example, let's say suppose gender is a feature space instead of the label. Gender, let's say, is a feature space, which is for example male female, and then suppose let's say your score, your final grade, which is A B C D, is another feature space, for example, and then we can use all those to label something, and then we can apply the categorical naive Bayes. Each feature space is a categorical set, meaning that they're discrete. The previous one is continuous. This one is discrete. Okay, and several things we can estimate the probability that feature J takes category RK is the number of samples with the label Y, and also feature J is in category RK, and divided by the total number of label. And actually, oh, I just realized I label spelled wrong. Actually, from the whole course, you'll see the probability is estimated by what? By the frequency in the training data. So formally or mathematically, we can write it this way. Again, don't be scared by those notations. They're super simple, meaning just, this formula means this, the frequency. And the one thing is that to make it robust in a real world application, we typically, in application, we typically add this Laplace smoothing parameter S. And in the numerator, we add an S. In the denominator, we add an item which is S plus Mj, where Mj is the total number of classes here. Okay, so again, here we can just compute it. For the details of the mathematics, if you're interested, you can see here. But actually, it's super simple. Why? Because this is the posterior. I can already get the posterior, and then you just need to substitute everything to this formula. Then everything's done. Super simple. Here I'm not gonna compute by hand or something. Let me just directly code it again. I need to cheat makes it easier. Here I'm gonna copy and paste. So now you need to also generate categorical distribution training data set categorical. Okay. Here I specifically wrote categorical distributed means integers or discrete data set. Okay, so here I have n equal to 50 still, and x1 equal to empty dot random dot rand int. That means give me a random number, integer number. It will be between 1 and 19. If I remember correctly, this one is inclusive and this 20 is exclusive. In other words, this should be between 1 and 19. I'm not quite sure, but super simple. We just search it down. It has the documentation here. High equal to none, size equal to none. So let me see here. Let me see here. High equal to none. Yeah, low inclusive, high exclusive. So that's the thing. So here, if I write 120, that means from 1 to 19, and then size equal to n2. N2 means I will generate 50 data. Each data includes 2D here, and then y1 equal to ones m np dot ones m. And you know what? We can actually have a look at x1. See, all of them are between 1 and 19. And each data is a 2D. 2D because, later our plot, plotted all this data, discrete data. That's why I need X and Y, and hence it's 2D. Okay, so now I just copy and paste for x2 and x3. And then the parameters for x2 is 20 to 40. And then for x3 is 10 to 30. I try to make them like overlap a little bit, but not too much. Okay, now I can plot the training data. Here gonna be the same. I'm gonna just copy and paste. Actually, all of them gonna be the same. Let me see here. The only difference is the model. The model here, I can no longer use Gaussian MB. Instead, I'm gonna have from scikit-learn.naive Bayes, I'm gonna have categorical MB. Okay, so training here is gonna be categorical MB. Okay, and now fit XY. Okay, one thing is that in the categorical MB, we can actually add the Laplace. Oh, it doesn't show me the documentation, but let's see here. Recall that here we can add the Laplace smoothing parameter. So the syntax says alpha. I can use alpha equals to 2, so that this tells Python that hey, the Laplace smoothing parameter s equal to 2. So now I'm gonna feed it, and all this is gonna be all this is gonna be the same. The difference here is that I didn't add here minimum -5 or +5. You see the difference before? Here I wrote minimum negative -5 +5 again because I want to leave some boundaries. But if I don't do it here, you'll see those points are exactly on the boundary. Okay, so let's just run that and see the result. Uh-oh, great. Model fit xy, y fit xy is going to be wrong. Negative, ne negative data. Huh. That's why. Because it's still using the x and y from the previous example. That's why it's wrong. I forgot to mp dot concatenate. And then, wait, where am I running? I'm running here, right? Not to the previous cell. Okay, so now negative. Why still negative? That don't make sense now. Wait. Belongs to yeah. Now I should not have any negative numbers. How could I have negative numbers here? Really? Let me print the x, and then I'm gonna comment everything here. Let me see the x. X equal to x1, x2, x3, x is equal to 0. Why can't I print x? Where is the negative value? No, there's no negative value at all. Then why it shows it's wrong? Let me see. Okay. I know why. Because of this. Okay. Now I understand that that's the reason why in this example I didn't include, the boundary because otherwise it would be negative. Okay, here we go. You see the difference? The difference that all these points are on the boundary. Similar things in this example, I can run it again. Uh, Here looks nice, right? Okay, let me show you. What if I remove this -5 or plus, plus something? You will see those points will be on the boundary. See it? Those points are exactly like here on the boundary. I feel it's just it's just my personal preference. I just feel it's kind of like pretty ugly, and hence I added this. It's again just personal preference. But here you have no choice because if equal to minus something, then it could be negative, which is true, and hence we have to keep this. And this is the categorical naive Bayes. Compared to this figure with this figure, what did you see? You can see this is are all like block wise, right? It's like it has many blocks. Why? Simple because it's categorical. Categorical means discrete. Discrete, hence we have those kind of blocks. So yeah, here we go. This is the categorical naive Bayes. Again, the important thing is when you are gonna apply categorical. It is the case that when those feature spaces are discrete. You cannot say, hey, what is your gender? Your gender can be -1, +1, or 0, 1, indicating male or female. You cannot say my gender was 3.14, 1950, 29, 26, which is pi. You cannot, you cannot make it like this way. So that's why it's a discrete set. Okay. The last multinomial, the last naive Bayes I'm going to introduce is M and B, which is not multinomial naive Bayes. Before it, we need to first recall the binomial distribution and a multinomial in the introduced multinomial distribution. So for a binomial distribution, we actually count the number of success or failure. Wait a minute, let me make it bigger. We count the number of success or failure from W independent identical distributed trials. And since the binomial, this bi means I have only two outcomes, either success or failure. Very simple. And let's suppose in each trial, the success probability is theta, and the failure probability, of course, is 1 minus theta. To make my life easy, I use another notation, which is CASI. Define CASI equal to 1 minus theta. Okay, so now the PMF, probability mass function of binomial distribution, is this one. I again assume everybody has learned it, in probability class, which is super simple. And I know the notations could be different. Probability class is typically n choose k, right? And then p to the power of x and a q to the power of n minus x, something like this. Here I just use another notation, but the meaning, is exactly the same. Okay, binomial here by, I'm gonna replace this by with multi, meaning that instead of having only two outcomes, which are success and failures, here I can have, let's say p outcomes. And then, for each outcome, the corresponding probability gonna be theta j. Here j is from 1 to p, indicating the p outcomes. To make it a valid probability distribution, I must have what? I must have theta 1 plus theta 2, blah, blah, plus theta k, p equals to 1, right? So now we're going to perform WIID trials, and then I will use this vector to record the number of times each outcome occurs. And here's the PMF. If X follows multinomial distribution here, instead of having only two parameters, which is the total number of which is the total number of trials and the probability for success in binomial distribution, here I will have p plus 1 parameters, which is first the total number of trials, W is still the same. But here, instead of theta, I'm gonna from theta 1 to theta p. In some textbooks, you can read it as theta 1 to theta p minus 1. They're the same, okay? The reason because I've already known this. So as long as I know from theta 1 to theta p minus 1, I can compute theta p equal to 1 minus the summation of everything. So they're the same thing. Okay, so here still it's gonna be, a binomial. Here we have a binomial coefficient here. We will replace it with a multinomial coefficient, and the rest is the same. Here there's no difference. Yeah, why? Because c equal to 1 minus theta. That's the thing. And here we go. And I'm not sure whether you have seen this multinomial coefficient before, but if you've not, here is the definition. It's just remember binomial. Binomial, let me see here. Let me say suppose I have, let's say, actually I don't know command how to insert one binomial formula here. Let me just do it this way to make it my life easier. Let me see where I cannot find. No, 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 no. Here. Let's say if I choose 3. Remember how to compute if I choose 3? Which is a 5 factorial over 3 factorial and then 5 minus 3 factorial, right? Which is what? 5 factorial is 120. Divided by 3 factorial as what? Is 6 times 2 factorial is 2. And hence is what? Is 10, right? And so here, the difference is that instead of, this, what I'm going to do is this. Let me just copy and paste. Suppose now it's 3, 2, no, let's say 2, 2, 1, okay? So what I'm gonna do is still 5 factorial, 2 factorial, wait, wait, 2 factorial and 1 factorial, which equal to 120 divided by 4 times, 2 times 2 times 1, which equal to 30. Okay, so that's the thing. They're equivalent. Why? Because this is actually this. This, I mean, it's actually this because the other number must be 2. Why? Because this 2 summation, this plus this must equal to 5. And hence you can make it like this. So you see what I mean? In other words, this multinomial distribution is nothing but an extension, for the where it is. It's actually an extension of the binomial, which is we replace by with multi. That's it. Everything, all others are the same. Okay, so now let's have a look at the counting feature. The counting feature, a feature is called counting feature if it represents the number of occurrence of something. This something can be, for example, an event, an item, or an object or something. For example, in the very first example, which is remember the email sensitive words, we count how many times each of the 4 sensitive words appear in a paragraph. These counts are the counting features. And this info counting feature is going to be used to classify whether the paragraph is appropriate or not. So a similar example is like spam email filtering, where we focus on some certain keywords and count how often each word appears in each in an email. Those counting features are widely used in those text classification problems. Okay, so why we mention multinomial distribution? Because now multinomial distribution is a natural model, probability model to represent such counting features. So here, suppose we're interested in P counting features. Later, I will show you a detailed example. P counting features, let's say P sensitive words in a spam, let's say in an email. Your task is to detect whether an email is spam or not. And that we have sufficient label training data for classification. Here I wrote a footnote with which as in real applications, large amounts of training data are always available. Let's say, for example, Google, they have hundreds of millions of emails nowadays. Every day. Be careful, this number, hundreds of millions, is pretty conservative because here, what I'm saying is human generated emails. Nowadays, using API, they, they can use, AI or robot automatically generate, I don't know how many. I even don't know the size, the scale of the emails. So I assume it's always, we always have the sufficient number of labeled training data. Then for a given class label, the probability of each outcome j can be estimated as a constant this, theta jy. And this j means, the jth outcome. And this y is the label, okay, class label. And then under this assumption, naturally, we can just assume that a feature space, the feature vector x follows multinomial distribution with these parameters. Here, assuming all the parameters we know, assuming especially those thetas. Later we'll introduce how to estimate it. But here, assuming everything is known. So now we have this model, and that's the reason why we want to introduce multinomial distribution because the multinomial distribution and the counting feature has a natural connection relationship. Okay, now let's have a look at an example. I know these notations may make people like dizzy, but here example may be easier. So consider a spam email filtering problem that focuses on 5 text features. So here, for example, we have these 5 words: dollars, selected, link, account, and a win. Suppose we have n labeled emails as training data for 2 classes. The 2 classes are spam or not spam. Very simple. Okay, so for each training email j, let x1, xi1 to xi5 denote the counts of the appearance of these, 5 text features. And then let yi be the class label of email, the training email I. Now we can model the feature counting, in this way, which is the feature space, the feature vector follows multinomial distribution with these parameters. Again, how to estimate these parameters we will introduce later, okay? Where this theta jy is the probability that text feature j appears given label class y, class label y, okay? So now is the thing. We have all these. W is super simple. We can just simply just count, for each email, how many features, in total appears. But how to estimate the theta, J, Y. And here we go. Again, we use the same idea, which is the frequency. So we have the total number of occurrences of feature j in the sample with label j divided by the total number of occurrences of all features. Be careful, here is feature j, and here is all features in the samples with label j, which is again, just frequency. And then applying the same idea of Laplace smoothing parameters. So if without smoothing parameter, it will be here. Let me just have a box here without the Laplace smoothing parameter, it looks like this way because the numerator is what? The total number of occurrence of feature j, see it? In the samples with label y, because here I have a delta indicator of y equal to y. This forces it to be y, to be this label y. Otherwise, this delta is 0, so you will not add anything. And how about the denominator? In the denominator, it is the total number of occurrences of all features. It doesn't matter like how many sample, what is the feature, it's a feature j or not. These are all samples where this wi is a summation of, given I of summation of xij, summation in j, which means the total number of occurrences of all features of data I. And now we apply the idea of Laplace smoothing parameters. Then in the numerator, I will add S. In the denominator, I will add SP, where P is the total number of features. Okay, so now, let me see here. Now everything looks good, and it seems that we can already, calculate everything. Correct. However, there's also an issue, which is recall that the probability, the PMF is here, right? And then we have this one. We have this multinomial coefficient here. And this number, if the W is large, it's extremely difficult to be estimated. Not to mention large, let's say 100 factorial is what? 100 factorial is already very difficult. I'm not sure whether you know starting formula or not, but in general, factorial is the same size, the same scale as exponential. You see what I mean? And hence factorial, if W is large, it's a very, very terribly large number that we cannot handle. And then, I mean, again, if something only theoretically beautiful, but it's not applied, what's the meaning of it? Meaningless, right? So here we can somewhat, somewhat use a trick actually to handle it. What is the trick? The trick again is the naive Bayes assumption. The naive Bayes assumption tells you what? Tells you, hey, under the given y, all features are mutually independent. And here what we wrote is, okay, so that in the given condition, all these can be gone. Why? Because they're independent of xj. So who cares you exist or not? So we have this, right? Okay. Now go back to multinomial naive Bayes. In multinomial naive Bayes, if we have all feature for a given y, or label y, all features are mutually independent. That means I can ignore all these, and then I will directly have xj equal to xj given y equal to y. And this is going to be much, much easier. Why? Because here, I only care about myself. I mean, this specific feature j. Who cares about all other features? Why I don't care? Because according to the naive Bayes assumption, they're all mutually independent. And hence, when I'm considering for feature j, I can ignore all other features. And hence, I can directly get this result. Recall that theta j theta jy can be estimated here. Although the formula looks like complicated, actually it's extremely simple. Uh, and then xj is the total number of observation that the j appears. That I know both of them. So this will be much easier than this one. Why? Because I just need to compute one time, and I don't need to care about the multinomial coefficient. It's done. And then in practice, again, because exponential can be a large number, what shall we do? Logarithm. Remember what we did? To maximize the posterior is equivalent to maximize the log of the posterior. And hence this, theta hat jy to the power of xj becomes what? Becomes xj times the log of theta hat jy. And where this is here. Plus, don't forget this prior number, and the prior number is simply gonna count, be the count of this. Here, constant log of 1 over n is ignored. Why? Because it's a constant, so who cares? So we just compute this for each y in 1, 2, 3, 4, 5 till n, and then we will get m numbers, and then we will classify the target data under the label which has the highest log posterior probability. Done. Super simple. So that is the whole story of the categorical naive Bayes. Here I showed a simple example. Again, the previous example. So it's 7-2 2. Okay. So now let's see a typical email, a spam email. Congratulations, you have been selected to win $100,000. By the way, nowadays those kind of spam email they become like 5 million, maybe $500,000 too little for many people. So I mean, for me, it's still enough. If someone can give me 500,000, I will be very happy. Of course, it's a spam email. You have been selected to win 5 million. Sorry, $500,000. Okay, click the following link to create an account and claim your reward. And you know what's going to happen if you click it? It will first steal your personal info. It will ask you a lot of questions about your personal info. It will steal your info. And more ridiculous thing is that it will tell you, oh, in order to transfer you 500,000, you need to pay a small amount as a transfer fee or as like a tax or those kind of stupid things. And then you will, your ID or your personal info will be stolen, and then you will be stolen those amount of dollars. So this is those kind of spam emails. Okay, now we want to use machine learning, use MNB naive Bayes in detail multinomial naive Bayes to automatically detect this is a junkie, this is a spam email. What to do? Okay, first of all, suppose we're interested in 5 features, text features, which are dollars, selected, link, account, and win. These are 5 keywords, sensitive words. Okay, now, excuse me. Now, for each of the n training emails, let x1, xi1 to xi5 denote the count of these features. The data is uploaded in the class folder, which is here. You go to lecture 7 and it's right here. Okay. So now uh where it is here. And the last column of the data, let me open this data. Sorry, just where it is. There we go. Okay, so the first 5 columns indicate how many times, each row is an email, okay? But I'm gonna encode, the email to this training data, where the first 5 columns indicating how many times the sensitive word appears. For example, in this email, dollars appears 1 time, selected 1 time, 0, 0, link 0 time, account 0 time, win 0 time, and the spam or not, this is the label Y. So in this case, these emails are not spam. That is the thing. And here I set the smooth parameter to be s equal to 1. So again, we can estimate the probability of the occurrence J by this formula. Okay. The details I'm not going to compute. You can just compute directly. Let me see by yourself if you're interested. But here, I guess it's better for us to skip the detailed calculations, which I forgot. Uh, I probably write a code to compute it, or maybe I can just directly use Excel to compute it. It's actually super simple. You just need to put it, the formulas in Excel, and I guess you can automatically compute. Okay, so now for y equal to 0, which is a non-spam email, I have the parameters theta, theta 10 to theta 50 here. Okay, then for spam, y equal to 1, I have theta 11 till theta 51 here. So now I've already computed all these parameters theta. Okay, so now let's encode this target email. So first of all, we are gonna count, right? Dollars selected, link, account, and win. So we can see, okay, let me just underline it. Okay, dollars one time, dollars two time, and hence I have dollars appears two. And then the features are what I forgot. Selected link account win. Selected, we don't have selected, and hence selected is what the selected is 0. And then you can do the similar things, which is let's say, does it have link? It doesn't show link, right? So link, the number appearance is 0. The next one is account. You see I have an account here, so account is 1. And the final one is win. Do we have a win? Win is here. Win, and so win is 1. And hence we have encoded this email to the training vector, which is 20011. Okay. And then for this training email specifically, what is the W? W is the total number of features. So 2 plus 0 plus 0 plus 1 plus 1 equal to 4. Next, we are going to use the fitted, theta hat JY to compute. Okay. So now here we're going to compute the log posterior. The log posterior, again, by omitting this constant is you just, substitute the number and then you will get for not spam probability equal to 1, not spam for the label y equal to 0, the log posterior is negative 1.4. For spam, which is the label y equal to 1, the log posterior is negative 0.922. Which one is bigger? Here, be careful. I'm not asking for absolute value. I'm talking about the number itself. Clearly, negative 0.09 is bigger than negative 1.4, right? And hence, we're going to take this label, which means this email is a spam email. Done. So this is the story. Again, if you're interested, you can just use Excel to let me remove everything. You can use Excel to compute everything. I did use email. I did use Excel to compute all these data actually. So so this is the thing. Okay. So after finally we're gonna use we're gonna use Python to compute an example. Here I need to upload the data first to the server. Okay, here we go. It's pretty fast. And now what I'm gonna do is I'm gonna copy paste those things. Actually, I don't need so many libraries. Let me see here. I don't need this one. I don't need matplotlib. And here I do need the multinomial. Multi, oh wait, maybe big multinomial. Yes, here we go. And then I'm gonna have data equal to PD. Wait, pandas. PD dot read CSV. Okay. And then this name, whatever name. CSV. Okay, so I actually go to data.job. And then let me see, what is the name of it? Spam question mark. Okay. Spam question mark. Access equal to 1. And then y equal to data spam. Okay, so now I'm gonna have what? The multinomial naive Bayes classification, or let's say training model training. So I'm gonna say model equal to multinomial and be whatever. So here again, similar to here, I can set a alpha as a what? As the Laplace smoothing parameter. Here I believe I chose alpha equal to 1. Yes. Alpha equal to 1. Okay, so model dot fit y. Okay, so now I've trained it. So now we can, for example, test a data. So let's test this data, which is 20011. So I have X test. And let me write a comment here. Test data for NMB prediction. So X test equals to 20011. Be very, very careful that in the scikit-learn, it automatically, by default, it will automatically set up this one to be 2D. Why? Because you can test different, labels, let's say 11111. For example, you can test them simultaneously. And hence, even if your test data point is a single data point, you still need to set it up in 2D. Otherwise, it will show you error. Okay, so now I'm gonna have what? I'm gonna have model predict, right? So if model dot predict all the test data, test, and this will give you a 1D array. Since we only have one single data point, it's gonna be the zeros. If this equal to one, that means what? One is spam, I believe, right? Let me see. Yeah, one means spam here. Zero means not spam. So if it is one, then the label is spam. Else, label equal to not spam. So now finally I can print the test email as label. So this is a warning, it doesn't matter. If you don't want to see the warning, simple import warnings, warnings off, I believe. I forgot the details, but let me see. It may tell you wrong. Let me see. Five don't show warnings. Let me see here. Import warnings and then warnings filter ignore here. And to why not show the warning message, the test email as spam. That's it. You can, of course, let's say one, and then you can just let me just move all this. Why the mail still? Sorry, so sorry. And let me just print it. Directory print the test, the model dot predict x test. And you can see 1-0. That means the first email is a spam email. The second one is not a spam email. I'm curious, how come all of them appear means it's not a spam email? Well, I'm not sure. It's right. It's related with our training data actually. Okay, so this is how we can handle the multinomial naive Bayes. And finally, about this is how to determine the features after data collection. Because here I still give you the 5 features, which are dollars, select, link, account, win. But if I just give you, let's say, tons of emails, so let's say 1 million emails, how would you handle those, how would you determine the features? One method, if you want, a common method approach is to consider all unique words that appear. Remember in lecture one, no, lecture two Python, we showed, write a function, which is to build another list and then add you if is in it, then do nothing. If nothing, then add. Remember it? So we can get all the unique list. I know it's big, but it's doable, and appear in the training data, and then we just do it. Uh, People may argue that hey, this is gonna lead to a very large amount of features. True. However, the computational task is very manageable. Why? Because after logarithm and after application, after the naive Bayes assumption, the computing here is super, super simple. Here I even listed the computational complexity. It's only this one. So it's a fully durable. And that makes naive Bayes a very, very powerful classifier in practice. And you will, I mean, later we'll see more examples. You'll be surprised, like KNN and naive Bayes, they're so simple, but the result is, in many, many cases, are very, very powerful. Okay, so this is the simple introduction of naive Bayes. Next, we will continue to introduce another classifier. which is logistic regression. Everything's here as well. For my convenience, I will directly open it here, to for the logistic regression. Oh, wait, question, sorry. Can we extend getting over homework submission? Um, I'm afraid not that on Thursday, I mean last Thursday, not today. I've already specifically mentioned it. We probably don't want to extend the submission, and I asked, to start the homework ASAP. I know if you're not familiar with Python, I know it may take some time. So, we will still have homework too. But honestly, I would prefer not to extend the homework submission. Well, if you can, by 12, again, MDT, by 12 today, if you cannot finish it, you can just submit what you have finished. You know what I mean? It's better than nothing, because really, I've given 1 week instead of 1 day for the homework. And for the final exam, you will not have 1 week. Of course, you will not be given under 1 day as well. So, finish the tasks on time. Okay, so here we will introduce another classifier called logistic regression. In the logistic regression, so first of all, we have already introduced KNN, we've already introduced the naive Bayes, and we can see that naive Bayes classifier is actually under the frame of probability. Then before it, we've introduced a linear regression. Here we try to actually link the ideas of linear regression with a probability, frame, and this is actually the basic idea of logistic regression. So let's have a look at here the fundamental idea. So recall that the basic formulation of linear regression is in this way. I know for the notation before I wrote it as y equal to beta 0 plus beta vector t transpose times x. The reason here I use c is because later, I mean, y will be frequently used as a label space. And hence, I just don't want to make a notation confusion. And hence, I use another notation c here. Okay, so here c can in general can take any values on the real line, which is oops, sorry, which is which is negative. Let me make it silent. Sorry about it. Which is from negative infinitive to positive infinitive. And then suppose we have a fixed number of classes, let's say again m classes, from 1 to n. In general, if we want to make it, apply this linear regression idea in classification, we need to what? We need to map this real line into a discrete set, 1 to n, right? In general, this is not a simple a simple task, and it's not straightforward. And hence, traditional linear regression model cannot be directly applied to such classification assumptions. Interesting thing here is that most classification methods covered in this course are derived from basic linear regression model. In many cases, it's just a change. For example, I didn't explicitly mention in naive Bayes. Actually, there's a transfer between naive Bayes and the linear regression model. As long as you apply some tricks, yes, you can prove that these two are equivalent. However, you cannot directly apply it. You need some tricks. So in this lecture, again, we will use, x, bold x a vector, denote a random covariate or random, feature vector, and a y to denote a random class label. If I wrote a lowercase of x, that means it's a realization. Similar, lowercase of y, that means it's a realization of the label. Okay, so in this lecture, we will apply multi-nully, not multi-nully distribution, and then we'll use the vector notation y equal to y to fit parameters for logistic regression later, slides 7 to 8. Here's slide number 2. Okay, so an intuitive idea for the improvement to handle this issue is that we need to, include the concept of probability and classify a target data into the class with the highest post-tier probability. But the problem is that in the left-hand side of linear regression, the domain is the whole R line, then how can we, you know, map the probability space into like the whole line and then to make it, right? And so this fundamental idea behind it, everything here is called logistic regression, LGR. And what we do, we actually apply a trick here, which is we take a logarithm and then we, use two probability, px and qx, where px and qx are two probability mass function or two probability density function of x. And we assume this, qx to be greater than zero to make it valid. So we can clearly see that if we make this one, it will belong to R. It will, the domain of this log px over qx gonna be the whole R line. One question is, why do we need a logarithm? Why don't we, let's say, I'll make it easy. I just make it a px over qx. Why don't we do this? The reason is because px and qx are both probability density or mass function, and hence they are what? They are both greater than or equal to zero, assuming qx is not zero, okay? Let's say they are both greater than zero, and hence you can only get positive numbers. You cannot get negative numbers, and hence I need a logarithm. Once I get a logarithm, it can be, the log of something where something is from zero to positive infinity. After a logarithm, what the value the domain of log of this is the whole R line. That's why we need to have the logarithm. Okay, now let's have a look at some ideas. So the logistic regression can be modeled in this way, and the numerator is, different labels given x equal to x, and the denominator is fixed. We call it as a reference. A wait, sorry. Here's in each denominator, not a numerator. Sorry. Here y equal to m. Here's a typo. I will change it. In each denominator, we use the last class as a reference. Of course, you say I just don't like the last class. I want to choose the first class, or I want to choose the second class. Can I? You can, but here's just for convenience. We choose. I would say without the loss of generality, and we choose the last class. And also, this system to keep it consistent with most textbooks, and hence I'm writing this way. Okay, so now I can make it in this way, and all these are nothing but, the right-hand side is nothing but the system of the linear regression, and the left-hand side of the equations is nothing but the idea here, okay? Okay, so now I have this, and if we just link all these together, we just, you know what I mean? Like I move, I'm first of all, I get exponential of both sides. Let me just write it down somewhere so that you're gonna be more clear. Oh, sorry. Let me make it smaller so that I can cheat. Let me use another page. So from example here, I have let's consider a class J, okay? So here I have log of, let's say, P over y equal to let's say J, given x equal to x uh, divided by this y equal to m, right? This one equals to what? Equals to beta J0 plus beta J x. Here there's a t. I have this. So what I can do is, first of all, I will get exponential both sides. So it will be this, after getting the exponential, it will be this thing. And the right-hand side is going to be e to the power of this, right? And then I multiply this p. I multiply this part to the right-hand side. And hence, I will get what? I will get p y equal to j given x equal to x. This one equals what? equals this times exponential of e to the power of this. I will have this one. So I have all these j's. And don't forget that it's right here. Be careful here, j equals from 1 to m minus 1, not equal to m, okay? Be careful that these to ensure this form a valid probability this distribution, the summation of this here includes m itself must equal to 1. And hence you see, I have all these things, right? And then I just sum of this up. And the right-hand side must be 1. And hence I can what? I can compute this P, the probability of the last class. You see it? Y equal to M equal to this. And then I just simply plug in this value into each equation. So I can get the posterior for each feature. You can see here for each class, not for each feature, for each class. So you can see here. Get a point? First of all, using this one and also this one, so I get the posterior for the last class. Then I substitute this to each of the equations. For example, for equation 1, I substitute this result, take exponential each side, and then move this one here. Then I get posterior for class 1, for class 2, for class n minus 1. And here we go, okay? So as a special case for two classes, the logistic regression model is in this way. Here I did use this identity, which is uh, probability y equal to 2 given x equal to x equal to 1 minus probability y equal to 1 x given x, because I totally have two classes. So we get a very simple explicit posterior for these two classes for LGR. Okay, so now I have class probabilities as follows. And important thing is that each of these observed training data points must belong to exactly one class. So now I have parameters like what we did in linear regression. Our parameters are this beta j0 and the vector beta j. How to estimate it? Remember, in least square linear regression, we use what? We just use the normal equations, which is nothing but a partial differential equations equal to 0, right? Why? Because it's a quadratic function, and hence the 0 point, which is the partial differential partial derivative equal to 0. It is at what? It is at this indicates the global optimization. Why? Because of quadratic. So we use the Lagrange dual. That's it. But here the problem is way more difficult. First of all, to model the label, I'm going to introduce the multi-Nully, not multinomial, multi-Nully distribution. So again, recall the Bernoulli distribution. The Bernoulli distribution models experiment with two outcomes. Also, again, success and failure. And assuming the probability of success is P, so then the multinomial distribution has this PMF. And indeed, the multinomial distribution, Bernoulli distribution. Indeed, the Bernoulli distribution is a special case of binomial distribution in which the number of trial n equals to 1. So that's from Bernoulli from a binomial to Bernoulli distribution. Similar things, we can extend the outcomes from two, success and failure, to P outcomes, which gives the multi-Nully distribution. So here I have P outcomes and the probability, the probability with each outcome is Pj. And to make it a valid probability distribution, we need to have the summation of all Pj's equal to 1. Okay, and this is the PMF for the multi-Nully distribution, which is nothing, just a production of all these. And then clearly we can see this multi-Nully distribution, is equivalent to a multinomial distribution with a total number of trials equal to 1. This is very, very simple. And one very important thing is this. We need to guarantee that each experiment has exactly one outcome. And hence the summations of sorry, I should mention this actually. And hence the summation of all the yi's must be equal to 1, where or yj's, where these yj's are binomial. This means what? This means among all these y1, y2 till 1n, right? There must be exactly exactly one, and the n minus 1 are zeros. And this is interpretation. A valid realization must contain exactly one and n minus one zeros. In other words, this is for binary what labels yj, it must be the summation of them equal to 1. Okay, so that's the point. And then let's see this multinomial distribution. How can we link this multinomial distribution to the LGR, the logistic regression? So here we have already mentioned, for these n training data points, we represent the label. We can represent the label to be an m-dimensional vector. And again, as what we just mentioned here, it's a binary, and wait. It should not be in RM. Sorry, it's multi. It should not be RM. It should be in the class of. I will fix this typo. What I mean is this. It should be here. It should be belong to the well. It should belong to the class of this. Let me see. How can I add a text? Oh, here we go. It should belong to this one, two, m. So why should belong to this instead of Rm? Here's a typo. I'll correct it after this class. Okay, so now we're gonna denote. We're gonna for each of these n training data points, exactly one element is one, and all others are zero. This means that each training data point must belong to exactly one class. So here's a simple example. If we totally have three classes and the label of training data I belongs to class 2, so the corresponding label gonna be coded in this way: 0, 1, 0. So it doesn't belong to class 1, it doesn't belong to class 3, it belongs to class 2. Here we go. Okay, so now recall the LGR model. First of all, we have this, right? To make our notation easier, I denote in PJ and then X and then with parameters this. Okay, so we can apply the multinomial distribution to LGR to fit these beta parameters by assuming the label vector y follows multinomial distribution with all these parameters. And with this piece, recall that we have already got the explicit form of this py equal to y, which is under the what under the discussion before. It is, recall, it's here. The PMF of multinomial distribution is this, right? Okay, so now suppose we have all these parameters, isn't it? The PMF is the multiplication of all these, right? Where yj is the number of the label here, and then we can have sorry, yij is a label here, but yij is 0 or 1. So from this y is y0, y1, y2, y3. And then we can expand it by two cases. Case number 1 is the label is m, so that I will have this. Case number 2 is the label is not m. Then it will be a multiplication from j equals to 1 to m minus 1. And then it will be this. So here we got the what? The PMF of this. But here we still have beta k0 and beta k vector. How can we figure out this one? Here we do not have normal equations anymore because we do not have an explicit solution. But we're going to use a method called maximum likelihood estimation, MLE. I'm not 100% sure whether you have learned it in the statistical class, but indeed MLE is one of the most popular, point estimation methods. So the MLE, the model is, suppose we have a probability distribution with PMF or PDFF. This actor is a variable, or you can claim it like a training data something, and the theta contains the parameters to be estimated. For n observed data, the likelihood function is defined by this way, which is nothing but a multiplication of all the PMF or PDF of all these n training data, this observed data. Then the MLE chooses the parameters vector theta by what? By maximize by maximizing this likelihood. So the underlying or the principle of MLE is that the observed samples are representative of the entire population. And therefore, we select the parameters that make the observed data most probable, which means these parameters maximize the likelihood because we believe they're representative, and the truth is that we have observed that, and hence we want to try to say they are very, very representative, which means to maximize the likelihood. So this is the idea of the principle of MLE. Similarly, here we have multiplication, and we typically don't like multiplication because it can make our, calculation, more difficult. Why? Because think about this is PMF calculation or PDF calculation. It can make the number very small. Why? Because especially like PMF, it's between 0 and 1. Suppose I have a lot of training data, then if you brutally compute the multiplication, it can make the final likelihood function result value to be close to 0. Why? Because it will be 0.0000, many, many zeros, right? It's not good. And hence, similar idea, we take the logarithm of it again because logarithm is a strictly increasing function. So maximizing the log likelihood is equivalent to maximizing the likelihood. For more details, explanations, examples, you can just see the extensive reading here if you're interested. But here we're just gonna simply mention it and apply it to LGR. So again, we got this one for slide number 8, which is this part. Okay, so now we take the logarithm and we try to compute the log likelihood here. So again, by definition, it is nothing but a summation from I equal to 1 to n. Be careful here, n are the observed data, okay? Observe the data. And then you can get these, and let me see, let me just, you can get this. And let me see here, I just take the sigma out. Let me give me 1 second. I'm a little confused here. Okay, so these are, wait, let me make it bigger. So this item is this item, and then this part as this part. Finally, this part as this part. Yeah, I just put this sigma inside. So here we have two sigmas, for example. And the interesting thing is what? The interesting thing is you can see that the two items here can be merged. Let me use, let's say, a green color. You can see that here I have a log of this one, and here I also have a log of this one. They're exactly the same, see it? And hence I can merge this item and make it this way. And don't forget one thing is that for each training data, it must, it must fall in exact one class. And hence, for each I, the summation of all the features must be equal to 1. Recall here, where this, let me remove all this. Recall here, it must be equal to 1. And hence, I can simplify this item. I mean, after the class, you need to spend some time to have a look at it. Very interested in the calculation here. The whole item here equal to n actually, and hence we just need to choose the beta zero, J0 and the beta J vector that maximize the whole equation here, which is the log likelihood function here, then done. Unfortunately, it does not have a closed form or analytical solution. It's way more complicated than the case in linear regression, where we use the normal equations and we get a partial derivatives equal to 0 and we solve it. Here we cannot. So what we do is we will use numerical methods to compute this. And I believe yes, here in this one here, I introduced a method which is, let me see, I forgot where. No, 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 not here. Here. Yeah, it's a lot of mathematics. Again, it's not required. It's IRLS, which represents for iteratively weighted least square. Basically, it's just compute the weight and then move forward a step by the gradient and then do it again and again until a threshold, a boundary is get satisfied, and then we stop, something like that. But again, it's a bit too much for this short class. It's based on Newton's method, which is a very standard method for numerical calculation. Just in case, if you're interested, you can just read this, okay? The good thing is Python libraries from scikit-learn, it already provides built-in numerical optimization algorithms that can efficiently solve it. So we don't worry about this at all. So this is everything about the theories of logistic regression. Here is a summary of the logistic regression. So for step number one, we create this probability model and we get the PMF, the probability, posteriors for these M classes. Number two, we assume the label vector follows multi-nonlinear distribution with these parameters. The parameters are actually defined here. Where are they? Are uh, are actually defined here, which are the posterior probability, which is right here. We assume the y follows multi-nonlinear with those posterior probabilities as the parameters. Then for training data I, we have what? By the PMF of multi-nonlinear distribution, we have this, and we can split into two parts. First with class M, second with class J to M minus 1. Next, we use MLE to estimate the parameters beta k0 and beta k vector. And finally, we use numerical methods to estimate the parameter. So this is the whole logic, three steps of the LGR model. One thing I do want to mention, which is the relationship between logistic regression and the Gaussian naive Bayes. And actually, under these conditions, the two classifiers are equivalent, meaning they're exactly the same thing. So the three conditions are first, there there are there are two classes. Sorry, missed the two. I have so many typos in three typos already in this lecture. I'm so sorry about. There are two classes only, m equals to 2. Second, with the given label, all features are independent. This is actually the naive Bayes assumption, remember? And third thing is that for each feature j, given y, xj follows normal distribution with with the mean is mu jy and variance is sigma j. And this sigma j, does not depend, is not dependent on the class label y. And as long as these three conditions are satisfied, these two, LGR and GMB, are equivalent. Again, the derivation and the proof is actually in this lecture 6 again, whereas this is here. If you're interested, I believe it's the last one here. It's right here. Uh, there are some steps if you're interested. But the meaning is that as long as two features are independent, the covariance is going to be 0. And also the variance is going to be equal across all classes. And hence we have this. And this is the fundamental idea of the proof here. Okay, so next, I guess we can see the Python applications of naive Bayes here. So here I include the two examples. Example one is still similar things. I'm gonna cheat it. You know, by generating this, I can probably copy and paste. One second. Let me just copy and paste from here. Let me see what I need to change here. Clearly, I need to change from sklearn dot. Let me see. Okay, it's a linear model dot linear model import logistic regression. Come here, logist. It doesn't come. Just take regression. And then let me see here to generate. Oh no, I had better actually from here. Generate a Gaussian distributed training data, correct? Let me see whether parameters are the same. Looks like even parameters are the same. Oh, now here I use different numbers. You don't have to. I mean, here just to let you know that the numbers could be different. Let me see whether all those points are the same. Yeah, looks all the points are the same. Okay, now here is to plot the what, which is correct. And then here I'm gonna use model logistic regression, model.fix xy, and then I'm gonna print the training accuracy as model.score x, y. And here I'll make it a dot for f to show for floats. And then let me see here, I'm gonna plot all the training data. And then here, let me see, I generated those spaces, correct? And then let me first run it to see. I remember, what? Import is wrong. Line 3, how come import is wrong? Here, 50. I do correspondingly change the label generations, 55. Okay, so these are the things. And then here I also include a test data, which is test, x test equal to 6, 5 in my slides. Again, you need to make it a 2D array instead of 1D array, okay? Then you can simply just y test predict equal to model dot predict x test. Be careful here in my slides. I did use, sorry, too small. Here in my slides, I did use here where this dot as type int. This means I force the result to be an integer result. Otherwise, by default, it will be a float result, and you will see the class 1 dot, 2 dot, 3 dot instead of class 1, class 2, class 3. This is the reason. Here, let me see x predict dot as type int. So now I force it to be an integer, and then I can just print. And I need to first set np dots print options like this way. Okay, so now I can print the predicted probability of the three classes are of the test data. Wait, we can use predict problem, which is here. Actually, what here I want to say predict. You see, we have log probability as well. And here, log probability is not that intuitive. So we're going to directly say the probability of X test. And then we say the test data belongs to class. And now I can make it Y test predict at number 0. So now we can just make this. And here in my example, I even also included a plot of the test data. So here I can just plot, and then I can have x test data 0, 0, x test data 0, 1. And what happened? 0, 1. And then I use a kx, make it a cross, and the marker size equal to 10, and the label equal to test data. Okay, here. Let me see here. Marker. Where's my marker size? Wait. Marker size. Okay, here we go. So here you can see these, first of all, the uh, here this is 0.9985. You can see that this one dominates. And hence the test data must be what? Must be this class one, you see? Because all other things, it's very small. You can run different times because we get random data. Similar things, it's, we can see this is 0.9475. All others are very small numbers. And let's have a look at our slides to introduce more things here. Here, the first thing is training accuracy. The training accuracy is actually very simple. It's computed by, first of all, it will predict the training data and then compare the label with the true label. And then, we can compare the training accuracy. For example, in this, in my slide, we can clearly see five data are misclassified. These five data are, let me see, one blue here, which is this one. Let me use a yellow color. This one's misclassified. This one misclassified two, three, four. Why I found only four? Oh, five here. These five misclassified. And my total training data is 165. And hence the training accuracy is the corrected, classification among the training data, which is 165 minus 5, over the total training data, which is 165. And hence this equal to 0.9697. That is. And then the predicted probability for the three classes are this way. And hence the test data is, belongs to class one. That's the result. Okay. And I see it's already 7. So I still have one more example here. I will leave it to the next class. I mean, this will be super simple, which is, by the way, this is a real example, which is using credit card approval. Nowadays, I don't know, did you see if you apply a credit card, you just put your info there, you click submit. And typically, you just need to wait 30 seconds, sometimes even 10 seconds to show the result. Congratulations, your application has been, approved, or sorry, it's denied, something like that. How did it do? It is behind it. It's in many cases, it's the logistical regression actually. You may not believe 20 years ago, 40 years ago, let's say 1980s, if you try to apply for a credit card, you want to mail something, to the bank, and it takes typically 1 to 2 months. They will finish because they manually check everything and then mail it back to you. But now it takes just maybe 30, even 10 seconds because everything's by the logistical regression automatic. Okay, let's finish our class today here. Thank you so much for the class and see you on Tuesday.